lecture will guide you through how to choose the right statistical analysis for the project that you're working on. After completing this lesson, you will be able to select the right test for analyzing a set of data based on the scale of measurement of the independent and dependent variables in the study. There are several different kinds of statistical analyses out there. These can be separated into two main categories referred to as univariate and multivariate data analyses. The key differences between these two categories is that univariate analyses focus on tests that have only one dependent variable, whereas multivariate analyses focus on tests with two or more dependent variables. This entire course only focuses on conducting univariate analyses. The following 6 analyses are the most common types of univariate data analyses that are often discussed. Each of these produces a different type of test statistic. Let's review what's meant by test statistic. Every statistical test is associated with a computed test statistic. Oftentimes, we work with a statistical program that automatically generates this information, so we don't think too much about the mechanics about how things work. However, the first step in running an analysis is to generate a test statistic. This statistic represents the amount of shared variation there is between the variables in relation to the total amount of variation in the model. After computing the statistic, we use probability theories to determine if the test statistic we obtained was larger than what we would expect by chance. The bigger the statistic, the higher the probability that it did not occur by chance. When the statistic falls within a range that is below the 5% threshold of error, then we have enough confidence to say that it represents what is happening in the real world. This means it's statistically significant. This process is mimicked by all univariate data analytic techniques that we'll discuss in this class. But how they do it varies based on the types of equations and distributions used. Let's look at a couple of examples of this. Correlation examines the ratio between SP and SSX times SSY. These represent the shared variation or overlap between the variables versus the total amount of variability in X and Y. T-tests examine the difference between the means and how much total variation there is in the model. Similar patterns are seen with regression, in which the most important component of the regression line, the slope, is a ratio between SP and SSX, which is the shared variation between X and Y and the total variation in X. Finally, ANOVA equations also represent a ratio of the sum of square within treatments to the sum of squares of the entire model. I'm sure by now you've seen a theme. Even though they all seem different, many data analytic techniques are united on this one front. They all represent some form of shared variation to total variation in the model. Data analytic techniques also differ based on the type of distributions they use. After computing a test statistic, you compare it to where it would fall along a distribution to see if it is in the significant range. Different tests use different distributions with different shapes. This is just a sample of the different distributions used by different statistical tests. The fact that these tests use different distributions means that they're associated with different statistical assumptions. These assumptions are often tied to the nature of the independent and dependent variables. When selecting the appropriate test, it is therefore important to make sure you ask yourself the following questions to help ensure that you are not violating any of the key assumptions of the statistical test. What is the nature of the dependent variable? What is the nature of the independent variable? How many independent variables do I have? After answering these questions, you can then use this flowchart to select the most appropriate test. Note that this should be used as a general guide to statistical analysis, and that there are exceptions associated with the use of these techniques. For example, there are times in which categorical data can be analyzed with special types of correlations. Exceptions aside, this flowchart represents a good starting place in selecting statistical tests. To illustrate how to use the flowchart, let's run through an example together. Let's say I wanted to find out if groceries were cheaper at Walmart versus Y supermarket. I can restructure this question to clearly indicate my independent and dependent variables. The independent variable of type of supermarket is categorical with 2 levels or subcategories. These subcategories are Walmart and Wise. On the other hand, the dependent variable is the cost of groceries, which is a continuous variable. Using the flowchart, you can see that with a DV that's continuous, an IV that's categorical, and only has 2 levels or subcategories, a t-test would be the most appropriate test. Keep this flowchart in mind when thinking about what analyses to run, and remember that it's not meant to be a panacea. There are exceptions to these techniques. However, we will not delve into them within this course.